Today we're going to look at application of exponential functions, because in most of the time that someone's using exponential functions, there are going to be boundaries to a beginning and an end. So the domain is not always all real numbers. So let's look at these situations and then also just take another opportunity to look at and identify the parts of an exponential function, as that's going to be important for you. So right here we have a population of rabbits, and it's represented by this exponential function. It kind of has an interesting exponent. It's the time, which is represented by t, is being multiplied also. That's kind of interesting. And the number of months is t equals 0, which corresponds to January. That'll become important in just a little bit. So take a look at it again. And actually, before we even take a look at it, I want to go ahead and write the parent function here again. Kind of get used to that. I wish it was on your formula chart, but it's not. But it says explain that this function would be growth or decay. So what do you think? It would be growth because b equals 2.5. And if b is greater than 1, it's growth. So you want to be able to identify that pretty quickly when you're looking at an exponential function. And then it says, what is the y-intercept? So the y-intercept is your a, and here a is 200. So we're talking about rabbits, so it's the start population of rabbits. So again, I'm reading the exponential function and identifying its parts. So then they want to know the number of rabbits in March. Well, if January is 0, then February is 1, and March would be 2. So now that part comes in handy. So I'm going to use my exponential function. I'm going to plug this into my calculator probably. And I've got 0.02 times 2. And I end up with, what do I end up with? I end up with 207 rabbits. Very exciting. Now it wants to know in 1.5 years. Now I wouldn't expect you to necessarily be able to figure this out, but think about it. If January is 0, then 1.5 years is not going to be 18 months, because that would be your first guess, 18 months. But because January is 0, the time is actually going to be 17 months. So again, I have my formula. I plug in my t for time, 0.02 times 17, and I end up with 273 rabbits. It's very exciting. Okay, now, if I sketched this graph, it would look, again, I'll go ahead and make a coordinate plane. What this would look like is it would come up, as its growth, like this. And right here, that would be 200. But because that's actually just the beginning, this is the time that's moving. This is the number of rabbits, my x and my y. So here, the domain, well, first off, the asymptote is y is 0. The domain, is it all real numbers this time? No, the domain is x is greater than equal to 0, because we can't have negative time. And the range is started with 200 and continues to go up. Interesting. So that changed quite a bit there. let's go on to the next one. I'm looking at this as desktop computers that are sold at a particular store. And so we have this function right here. And it wants to know if it's growth or decay. Well, I'm looking at it and I see that B is less than less than 1, because B equals 0.85. That means it's going to be decay. So again, you want to be able to read that pretty quick when you look. What is the y-intercept? The y-intercept, remember, is A. I'm going to write that formula here again. Y equals AB to the power of x. And A is 380. So that is the number of desktop computers. Do we even have desktop computers in our school anymore? I don't even know. Are they all laptops down there? In 2010. Okay, so now I want to know 2020. 2020 is minus 2010 is 10 years. So that's what we're looking for our t. T is 10. So I'm going to take this formula and I'm going to, let me slide this down so I can see it. N equals 380 times 0.85 to the power of 10. So N equals, let's see, 75 computers. So the number's going down. I don't know who would buy a 10-year-old desktop computer out of this store anyway, but now they want to know 2050. Will there even be such a thing as desktop computers in 2050? So let's see. In 2050, that's going to be T is 40 years at that point. So N is 380. Remember, we're having decay. It's getting smaller, but it's not allowed to reach 0. Because when I put this 40 here, I don't get 0 or negative something. I get 0.57, which means I have less than one computer. And this is why it's kind of a silly example, but as the years go by, it just means I'm going to have less and less of one computer. But technically, I'll never get to 0 computers. It's kind of a silly example. I didn't write this problem. All right, so if I was sketching it, then you kind of like end up coming like this on like if you're on Desmos or on your calculator. And right here would be 380. And it's coming on down, it's coming on down. Here's my time. And this is my number of computers. Now, the domain here, we're not even going to do that. We'll go ahead and say that the asymptote is 0. But again, it's kind of a silly example. And then my domain, my x values, it's greater than or equal to 0 years, because I can't go any less than that. Range, also, I went on down to 0. Technically, it was never really got to 0, but it was greater than 0. But it was equal to 380. So they started with 380 and they went closer and closer to 0, but I guess they just got smaller, one computer. It's a silly example, but there you go. I hope you learned something. See you later. Bye-bye.